Hello, this is Craig Devine with Arcadis, and I'm here with my co-author, Dr. Tiffany Torralba, and we will be speaking about our new groundwater monitoring and remediation column titled Advances in Remediation, PFAS Precursors, Dark Matter Menace, or Negligible Nothingburger. Tiffany, thank you for joining us. And to kick us off, would you mind just providing a little bit of background on yourself and what you do at Arcadis?
Hello, everyone. So I have been with Arcadis for almost 2 years now. A little bit of what I do or the projects that I have been involved with are things like that vary quite widely, I think, in terms of the complexity. So starting with very simple projects like site characterization through, running fate and transport models up to more complex things like forensics or liability appropriation using modeling tools. So all of these has been based on the academic background that I have on modeling different types of organic contaminants. So things like munition compounds, chlorinated compounds, and most recently PFAS. So I kind of have used that academic background to provide tools for all of those different types of projects.
Yeah, fantastic. Well, let's start by addressing the timing of this topic. Precursors have been a hot topic for the last couple of years. And why is it relevant now for practitioners? There's been a lot of work in the academic circles, and now we're starting to think about it in the practicing community. What do you think has changed in the last few years, and how would you see that connects to the timing of this article?
So I think first it would be kind of good to define what we mean by precursors or what we are using as a definition for precursors in our article. So what we see as PFAS precursors are kind of non-terminal polyfluorinated compounds that through either biotic or abiotic transformation pathways ultimately degrade into terminal and commonly regulated PFAS, typically perfluoroalkyl acid, so PFAS. So this kind of really ties back to the opening section of our article where we talk about how the US EPA analytical method for PFAS, method 1633, has expanded what we routinely see as in environmental samples, but also what it still misses. So even with that expanded target list, the compounds we measure are often just kind of the end point of much larger transformation networks. So one of the first figures in the paper kind of helps illustrate that visually. It shows an estimated transformation pathway for a single AFFF related precursor, AFFF being aqueous film forming foams. So it is a single AFFF related precursor called 6,2-FTTAOS, and how many different intermediates ultimately converge toward a small number of terminal PFAS. So those steps include things like head group cleavage, where the non-fluorinated functional group is broken off, and then it includes a sequence of oxidation reactions that ultimately shorten the carbon chain. And then we present some chord diagrams that kind of zoom out and show that kind of funneling behavior is not unique to just that one precursor, but instead it is consistent across many different precursor classes documented in the literature. So I think what's changed is that practitioners are now seeing enough data, both from lab studies and from real sites, to kind of realize that ignoring precursors completely can mean ignoring a potentially long-lived, delayed source of the same PFAS or terminal PFAS that drive regulatory and remediation decisions. So I think that's what it has made them, kind of a hot topic, is just the fact that they are kind of funnel into the type of PFAS that we have to be all the time worrying about.
That's a great setup. And I really like that first figure, just highlighting the complexity and the potential pathways that are present for just a single precursor compound. And of course, many of these PFAS sources are a mixture of many, many different types of PFAS. And so the potential for a number of these sort of complex pathways that may have different rates, and those rates may be dependent on environmental conditions that vary, just underscore the complexity and potential importance of this challenge. Yeah, so we set the article up sort of acknowledging that there is uncertainty on the importance of precursors from a practical perspective. We see evidence, empirical field evidence, as well as a basis scientifically that precursor mass in some settings can be significant, and it can drive important behavior in the context of our remedial decisions and the typical life cycle of a remediation project. And then you also see evidence that in some cases that precursor mass may be small or it may be large, but from a practical perspective as it relates to mobility, risk assessment, and ultimately transformation into regulated compounds, it may not be important, the so-called Nothingburger. So in our article, we sort of present examples of situations where both of these things may be true, and then of course, provide some thoughts and recommendations on what that means from a practitioner's approach to a problem. But maybe we can start with the case or an example case where precursors do matter. What does the science and field evidence tell us about situations where ignoring precursors could lead to bad decisions?
As you mentioned, that is the focus of case 1 in the article. So a big part of that evidence comes from transformation kinetics, which we summarize in one of the first figures in the paper. So when you look at reporter half-lives across the ITRC precursors database, which is the database that we are using in the article from the Interstate Technology and Regulatory Council. So you see on that figure clear differences by chemical class in terms of the half-lives of precursors. So fluorotelomere alcohols, for example, often have relatively short half-lives under aerobic conditions because they are readily oxidized first to aldehydes, then to carboxylic acids, and then eventually to perfluorocarboxylic acid. So, but in contrast, things like sulfonamide or sulfonamide-derived precursors tend to have much longer half-lives because their transformation often starts with slower kind of nitrogen dealkylation and sulfur oxidation steps, which can be rate limiting, especially under anaerobic or very low energy conditions. So that kind of class dependent behavior is why the half-life distributions in that figure that I mentioned span orders of magnitudes rather than just clustering around a single value. We also included in the article a field example. It's one of the later figures in the paper from an AFFF impacted site in Michigan from one of our own projects. So on that figure, you can see precursor fractions kind of decreasing near the water table and with distance from the source, which is consistent with oxidative transformation and downgrade and conversion. So these kinds of spatial patterns are exactly what push precursors from just a theoretical concern into a practical one for conceptual size models, for long-term plume evolution, and for remedy design and performance. So I think that's kind of the case 1 that we try to make in the article.
Yeah, thank you, Tiffany. That's a great example, and the field data are quite compelling that in that case, precursors matter, and we see evidence of their transformation in the field at scales, time scales and distance scales that we care about. And that's consistent with some work that suggests that the presence of some current PFOS and PFOA plumes is largely driven by the transformation of historical precursors. That is, much of the PFOS and PFOA in those plumes wasn't originally PFOS and PFOA. It's been transformed to that, and that the remaining precursor mass has the potential to sustain those plumes for decades or longer. Correct. So on the other hand, the article also makes the case that precursors don't always deserve center stage. So when does the evidence suggest that their importance may actually be limited or maybe insignificant in the context of risk and regulatory drivers?
So that's the other side of the coin, I guess, that we lay out in case 2 in the article. So again, that one figure of the first ones in the article that I mentioned is really instructive showing kind of the half-life, the range of half-lives. So while some precursor classes show relatively short half-lives, others, particularly kind of the larger, more polar or charged compounds, transform very slowly in realistic field settings. In many anaerobic systems, for example, key reactions like oxidation or beta oxidation type chain shortening are very strongly suppressed. So it's very unlikely to see those kind of transformations. So from a reaction standpoint, that means precursors may get somehow like stuck after an initial step. So you might see partial head group modification, but not the full sequence of reactions needed to generate mobile and regulated PFAS or terminal PFAS, things like PFOA or PFOS. So when that happens, the compounds kind of remain sorbed and localized rather than contributing to plume mass flux. So that's why some field studies show precursors kind of concentrated in source zones with very little downgradient signal, and add in strong sorption and very slow desorption kinetics, and the practical impacts on kind of a near-term groundwater risk can be quite limited, even if the theoretical transformation pathway exists. And also if you add to that the analytical limitations that we also discuss in case 2 in the article, where we point out that many precursors lack validated methods or standards, and it becomes clear that kind of exhaustive precursor characterization everywhere at a site can introduce kind of uncertainty without necessarily improving decisions or necessarily contributing to informed decisions. So I think that's kind of the other side that we wanted to also highlight.
So given these two perspectives, or maybe extreme conditions, and of course we can have situations where we're somewhere in the middle, what is the practical middle ground or recommended pathway we're suggesting is appropriate for practitioners? How should we approach precursors at a typical site, given what we know today?
Yeah, so that's kind of the third portion of the article where we kind of reconcile the two views in that section. So the takeaway is that precursors aren't uniformly important. They are context dependent, class dependent, and process dependent. So the article as a whole shows that you can't assign a single degradation rate or mechanism to precursors as a group. So practitioners should, I think, start with kind of routine method 1633 monitoring, and then layer in targeted precursor analysis where site history, AAAF use, or spatial trends suggest they matter. So you have to kind of ask, what precursor class dominates at my site? What reactions are likely under site conditions, and which of those reactions could potentially be the rate limiting step? If kind of the dominant precursors at your sites are classes known to undergo relatively rapid aerobic oxidation, like fluoroethylamine alcohols, for example, and you have oxic conditions or remediation that introduces oxygen, then transformation terms probably should go into your CSM, into your conceptual size models, and other kind of fate and transport models that you are working on. If, on the other hand, the dominant compounds that you see as precursors at your sites require kind of slow nitrogen dealkylation or sulfur oxidation steps, and are in addition kind of strongly sorbed to the soil, then their short-term impact may be minimal. And so the figures in the article, we try to kind of put them collectively to show why spatial context is so important. So if precursor fractions decrease with distance while terminal PFAS increase, then that's a strong indicator that transformation should be included in the CSM. If precursors remain kind of sorbed near the source and don't appear downgradient, then source containment or, mass removal may be more appropriate than plume-wide treatment. So basically the bottom line is that, which is also what we state in the article, is to measure what matters and, use transformation tools like total oxidizable precursor very selectively, apply conservative rate assumptions in models, and anticipate that remediation can change PFAS speciation. So kind of that balanced approach should help avoid both kind of underestimating future risk and over-investing in data that won't change decisions, or it won't help really assessing the needs of your site.
Yeah, that's a great description of a measured and risk-managed approach. Well, Tiffany, thank you so much for this conversation and your efforts leading this article. Before we close, was there anything else that you'd like to comment on or thoughts for the future with regard to precursors?
No, I think maybe just for readers and I guess listeners, just our figures in the article are meant to be kind of practical tools, not just illustrations. So they show how precursor chemistry, transformation, and transports intersect at real sites. So we encourage practitioners to kind of use those figures as a framework alongside, of course, the actual article when you're developing conceptual site models and remediation strategies. So they are there to be a tool for practitioners to use.
Fantastic. Well, thank you very much, Tiffany.
Of course. My pleasure.